All right, taking a look at 8.4 today. And we were talking about equations of sinusoidal functions. Okay, so we've been talking about sine. We've been talking about cosine. We've been talking about the fact that both of those graphs are sinusoidal, and they have this periodic property to them. They go up and down, maximum, minimum, and they're very repetitive. And so any graph that appears to be some form of a sine graph, whether it's stretched out this way or moved up or down or left or right, any kind of graph that resembles a sine graph is called sinusoidal. And so today what we're going to do is we're going to explore all of the different types of variations, really, of, let's say, like a sine graph. So this first question is, if you were given an equation like this, y equals 3 times sine x plus 2, what would be the maximum value, the minimum value, and the range of this graph? So in previous lessons, right, we've talked about the period, the amplitude, the maximum and minimum value, and the midline. But we haven't explored too many differences of really the variations of sine. We've just been talking about sine or just cos. So we're going to talk a little bit more detail now about these different ones. So what we're going to need to do is you're going to need to get a graphing calculator. Those of you at home, you can grab a graphing calculator if you have one on your computer or of your phone. Take a moment to grab one, and you guys in here, grab a graphing calculator, take it back to your desk. And what we're going to do is we're going to graph this y equals 3 sine x plus 2. So if you have a TI-83 like me, it's going to look like this. Got one? Okay. Get it out, crack it on, crack it open, turn it on. Y equals 3, froze up. There we go. 3 sine, now this is your x button, remember, x. Close those brackets off, because this plus 2 is actually not inside the brackets with x. That's actually quite important. That's different. So just put a plus 2 on the end. Now, your window. Okay, the window. Let's just do zoom 6. That gets us a standard window. Oh, and this calculator, of course, if you have something like that, you're probably going to want to check to make sure that you're on. Now, for this graphing here, you have to be on radians now. We're going to put this on radians, okay? When we're graphing sine and cos, your calculator needs to be on radians. So let's try that again, and here we go. Now, we can still see this graph in degrees, but radians, we're talking about one regular period length of 6.28, right? In degrees, one regular period length is 360. So we have to really change our window to show hundreds and hundreds for x. So we're just going to do it in radians. Yes?
How do you change it to radians?
So to change it from degrees to radians in a graphing calculator like this, you're going to want to hit the mode button right here, and that gets you to this one. All right. Okay, so we've got that graphed, and this is what it looks like. So the maximum and minimum value, okay, maximum and min. Now, you might be able to guess what this is. It might not be a very detailed guess. You could hit the trace button, and that just kind of like puts this little cursor there on the graph. You could kind of try to get it to the very peak there and check out this y here. So we're at 4.99, which looks like it's almost at the very peak. Looks like we're coming around the other side of it, maybe. I don't know. It's tough to tell where the exact height is. Is it exactly 5? Is it 4.9? 4.99? What is it? So in order to do this exactly, I'll just do this real quick for you to show you. But I think we did this before in class. Second function, calculate menu, and you get to the maximum. Remember doing this? You could calculate a maximum point on any kind of local graph, any kind of like graph or part of a graph. You go left bound, yes. Move your cursor over to the other side of the maximum point and say left bound, yep. So now you're telling your calculator just to center in on this little area to look for the maximum value. And then what you could do, the third thing you could do is take that cursor close to the maximum that's in that little left bound, right bound area, and then hit guess. And it will give you the exact maximum. Okay, so it's max of 5. So you could have guessed 4.87, 4.99, right? It's going to be 5, but here's how you can be exact, okay? Now the minimum here looks like it's at about -1 or -1.5. Well, you know what? Let's do the minimum. Second function, calculate. Let's do number 3, minimum, and let's go over to this next minimum. So this is the left boundary that I'm going to set for my calculator. I'm going to cursor over to the right boundary, anywhere over there. And then I'm going to hit guess and ask the calculator to guess the minimum, and sure enough, it is at -1. Okay? At -1. So that's one way using your calculator graphing technology to do that. So if we have, let me just quickly draw this. So if we have a graph where, now where does it start and where does it end? Okay, it's a little bit, okay, so it looks like the start point of this typical graph is up a ways, right? Let's find out where that is on the y-axis. So let's just do second function, calculate a value. I'm going to put 0 in there, and that's going to give me the y-intercept. So 0, 2, okay. So 0, 2. Let's just start our graph there at 0, 2. Just, okay, just as a point there. So 1, 2. And it goes up, and it goes down like this, right? Something like that, just a rough sketch. It's going to go up to 5. It's going to go down to a minimum of -1. So right now we could state the range now. We've got the maximum value, the minimum value, and the range here is, what is it? It's, well, from -1, right? Less than or equal to y, less than or equal to +5. That's the range. And just for kicks, we could find the midline, which is halfway between 5 and -1, right? The midline, what's halfway between there? Well, that's a total of 6 units. So if I go down 3 from 5, I've got the midline at y equals 2. Right, okay, that's where I started, y equals 2. So y equals 2 is the midline. And the amplitude then is what? Amplitude is 3. Okay. All right. So knowing these things about this graph right here, this is going to help us to connect, okay, and this is the whole point of this lesson. You ready? This is the whole point. We're going to connect the graph, the sine graph, with its equation. So the features of the sine graph, we're going to find out where we can look in the equation to figure out what those features are. So for example, why does this sine graph not start at 0, 0? Well, because it looks like the whole sine graph has been shifted up. And shifted up about how many units? Well, it looks like it's been shifted up about 2 units because there's the middle of it. And the midline is y equals 2. So it looks like the whole sine graph has been shifted up 2 units. Do you see anything in this equation right here that might represent a shift upwards of 2 units? Anybody?
+2.
Yeah, okay, look at the +2 right here. Now that could be a strong indication that this means a typical or a regular sine graph should be moved up 2 units, okay? That's what we're seeing. We'll explore that further. What do we know about the amplitude? For a regular sine graph, what's the amplitude? Like y equals sine x. Who remembers that? Anybody? What's, sorry?
The max value minus the range.
Yes, it's the difference between the max and the min, and it's half of it, so the amplitude is right here, okay? So for a y equals sine x, this is y equals sine x right here, the amplitude is 1. You see, from midline to the maximum is 1 unit. So y equals sine x would give us an amplitude of 1. Y equals, where are we? Oh, here we are. Y equals 3 sine x plus 2. 3 sine x gives us an amplitude of 3. So is there anything in this equation that we should probably take a closer look at to say, hey, that could be the amplitude of my sine function? And yeah, it's this number right here. So there could be a connection there. Okay. All right. Good? Let's test a couple of those theories right away, okay? Let's test a couple of those theories. I'm going to flip over here to my Desmos, okay, my Desmos tracker. Now I've got sine, I got a sine wave up here. So here's the sine wave right here from 0 goes up to 1, amplitude of 1, comes down to 0 at pi, 3.14, and goes down to a negative 1 down here, and back up to 0 at about 6.28, okay? So that's typical. Now, let's see, where is it? Oh, A. Okay, so let's light up this graph here. So the blue graph is y equals a sine x, and I've got a set to 1 right here. You see that? So what happens if I change that 1 to 3? Boom! Look at that. So compared to sine of x, the amplitude for sine of x is 1. The amplitude for y equals 3 sine x is 3 units. You see that? So I can now make a smooth transition here back to 1, and you can see how this graph, okay, the a value looks like the amplitude. As the a goes up, so does the amplitude. See that? Now, what if a is negative? What do you think is going to happen if a goes into the negative? What do you think is going to happen? Tell me before it happens. It's going to what? It'll be like the cosine? Okay. Maybe a little bit like the cosine. Yeah. So look at the trend here. This is a very high a. I'm coming down, coming down, coming down to 1. Now I'm between 0 and 1. So when I hit 0, it's going to be a flat, straight horizontal line. What's going to happen when I hit negative? Well, it's going to keep going the other way, and it's going to flip. So it's kind of like a flip. It's a mirror. It's a flip around. Now is it kind of like sine-ish? Sine is not quite like this. Sine is shifted a bit, but okay, I'll take what you said about it. Kind of makes it a little bit more like sine as being a good observation. Okay. All right. So the point is, let's see, a equals 3 looks like this. Now, here's the d one over here. You see that? Sine x plus d. Okay, sine x plus d. I'm going to take this one off now. Let's see what happens if I make this d 2. Okay, 2. And I'm going to light this one up. And look at that. The black graph is exactly 2 units higher than the regular sine graph at every point. And so as d gets larger, the whole graph moves up. It translates upwards. And if d goes back to 0, it's the same, and negative goes down. Okay? All right. Okay. So let's test this theory out with our y equals 3 sine x plus 2. And notice that I've got a lot of different parameters down here. I don't know if you can see this on the far left here, but I've got a lot of different parameters here. There are 4 parameters we're going to study today. A is one of them, and D is one of them. So guess what? Let's light up this graph right here, and I've got A equals 3. That's perfect. And I'm going to also let D, so it's going to be reflected in this equation here, I'm going to let D equal 3 sine and then 2, right? So look at it's moving up to 2 right there. So this graph, whoops, that's not what I wanted to do. Sorry. This graph right here, the blue one, is the same as this graph right here that we've drawn. Okay, we drew one period of it. Okay, so it's shifted higher, and it's got quite the amplitude. Okay, so this purple graph, and that's 2 right there, 0, 2. Okay, any questions? So A stretches, or A compresses the sine graph. Think about it that way. Pulls it up, or it compresses it down, but it's all in the vertical direction. And D doesn't stretch, but it just moves up, translates up or down. Okay, it doesn't change the shape, it just changes the position. That's A and D. Okay, so we'll go back to the notes here, and I want you to write this down. So this is the sine graph, the regular old sine graph with all of the parameters in the equation. And I'm going to zoom in here. Okay, so y equals A times sine of, now this gets a little confusing here, so let me just pause on here. We have some things going on here. We have a number that would be multiplied by the x. Okay, so that's what the b is. And it's convenient from left to right, A, B, C, D, right? So B is multiplied by the x, and C is subtracted from the x. And you do need two sets of brackets here, okay, just to keep the B and the C all straight. So just copy down what you see here, and then the plus D on the outside, okay? So changing these parameters A, B, C, and D will change the sine graph, okay? And we can make any sinusoidal graph, we can create any sinusoidal graph by changing just those four parameters, okay? It's gonna be excellent. All right, so let's summarize a little bit about what we learned already about A and D. So these are the notes that you can take. I've just made some blanks here. So y equals a sine x. Okay, what should we put in here? A is this is called the vertical stretch. So it doesn't just move the graph, it actually stretches it. It stretches it vertically like this, it pulls it apart. If A is greater than 1, okay, it stretches, and yes, I know I called it a stretch, but it stretches vertically. So it actually pulls it apart, pulls it vertically. And I'm going to use a different word here for when A is between 0 and 1. That's going to be more of a compression. Okay, so compression. It compresses vertically. Okay, that's A. So those are the notes for A, which we've already discovered. Let's zip, oh, actually I should finish this. So the absolute value of A, that is if we disregard the sign positive or negative, if we just drop the sign, the absolute value of A is the amplitude, okay? That's another thing that we talked about here. A is the amplitude. And, sorry, you probably don't like that color in this up there, do you? I will use a different color after this. Okay, so that's A. Now I'm going to actually skip down. Did you guys get that for A? Can you grab that door for us, sir? Ryan, too. Now I'm going to skip down to the D part because we've already taken a look at the D part. Okay, so the D here, that's these ones. That one's whoops, didn't mean to disappear. That one's easy. D is a vertical. Now we're going to use the word, and I'll put this in yellow, translation. Okay. And remember from our work in this already, a translation means that it just moves from one spot to another. It just moves. It does not stretch or contort at all. It just moves. So the graph moves D units blank if it's positive. So what word should I put in there? Anybody? The graph moves if D is positive. So if we have plus 2, like in our example, it moves up. Very good. Oops, I said I was going to use a different color. I tried to change it. Up if it's positive, and it moves D units down if negative. Okay. So that's the vertical translation. Awesome, you guys are doing great. We're going to talk about B and C now. And I'm going to flip back over to Desmos here. So B and C, forgive me if you weren't done that, I'll come back to that screen. But let's just take this one point at a time here. Let's talk about B first. Sine of bx. You see that? Now I do have the sine graph just here for reference. That's the sine graph, okay? 0 to 2 pi over here. Now, if I light up this y equals sine of b times x graph, if b is 1, we have just a regular sine x graph. What happens if I increase b? Well, just watch. If I increase b, look what happens, the blue graph. Look at that. It's actually compressing horizontally, okay? So as the b gets larger than 1, the graph actually squishes up or compresses horizontally in this direction. Okay? Now that's b equals 2. And I want to ask you a question. What do you notice about the purple graph if I highlight x equals 0 and x equals 6.28? Notice that the both graphs cross 0 and 6.28. What do you notice about the purple graph as opposed to the red one now? It's smaller, yes, it's compressed, okay. Anything else you notice? How many times do you see the sine graph now in 0 to 6.28? Okay, the period is shorter. Yes, the period is smaller for this graph now. That's exactly right. Look at that. It goes one complete cycle in half the time. So I'll go back to my question that I just asked. That's a very good observation. Do you guys notice that there are actually two complete sine graphs in what would normally be one period length for a regular sine? So look at this. If I go to 3, how many complete cycles of the sine graph do you have now in 2 pi radians? You have 3. See that? Okay. And of course, if I went to 4, there would be exactly 4. So 1, 2, 3, 4. So 2 things. The b value, it squishes up the graph, making the period length smaller. And that number, you can think, that's how many regular sine graphs I now have in a regular 2 pi period length. Okay, so let's go back to our notes. Let's do that b. Where's the b? Oh, it's up over here. I'll move over for the b. So b is called a horizontal stretch. I'm going to call that a horizontal stretch. All right. Okay, so if you take the b value there and you do 1 over b, that is a stretch, or really it's a compression. So depending on what the b value is, that's the factor by which you stretch it out, or the factor by which you compress it. What I mean by that is this. If we have a regular old sine graph like that, sine of 2x looks like this. See, we're compressing it by 1 over 2 because 2 is b. So the factor is 1 over 2. It's half as big now, half as wide. If I have, guess what? If I have sine of 1/2 x now, then my graph is actually like this. It's twice as big. So the period length, or the horizontal length of it, is 1 over 1/2, which is the same as 2. Now I'm going to get to that here in the notes in a couple lines down. So let's just continue. The number of sine graphs to fit inside of 2 pi is also that b value. So don't worry about positive or negative. We're just dealing with the magnitude right now. Mike, write this stuff down, man. Okay, well. All right, period length. The period length is the length from beginning of one cycle to the beginning of the next, right? Or to the end of that cycle. And that's going to be 2 pi divided by b. And that's going to be really important for us. 2 pi divided by b. Okay? All right, any questions there about that? Okay, finally C. Let's take a look at C then. Finally C. All right, now C is what we add or subtract to x. Now it shows as a subtraction. It shows as a subtraction. That's important. Okay, so this is a horizontal translation here, okay, or a shift. It's a horizontal translation or a shift. Now, let's take a look at Desmos here. Okay, let's get rid of that one. Here's our x minus c. So if I light this one up, if we have 0 for c, that's just sine of x. If I have x minus 1, look what happens. The graph is shifted to the right 1 unit. So notice this is x minus 1. X minus 2 shifts the graph exactly 2 units to the right. Okay? Now, here's something interesting. If I were to shift this graph far enough, I could get this looking a lot like a what? Cosine graph. Oh, okay. Cosine graph. So let's back this up. Here's the this one's pretty close too, right? There's a cosine graph. So this c value here, negative 1.5 or so. Now if I go minus, so here's 0, if I go minus, that means it's like x plus this number, you see? X minus a negative. So when it shows up as x plus something, that means it's moved left. And yes, the sine graph is about x plus 1.6. That now equals the cosine graph. So here's the cosine graph. See that? It's almost exactly the same. Okay. All right, so let's do some summary on the c. Because of the format, the sine equation is y equals sine of x minus c. So if we have sine of x minus 90, that moves the graph 90 degrees to the right. Right. That means, so what this means is it's x minus a positive 90 degrees. Okay? So if you think about c being positive 90, it moves it 90 to the right. But it shows up as x minus 90. So if you look at this number and this sign, it's opposite. If it's negative, we would normally want to go left, but we actually have to go right now. Okay? And sine of x plus 90 means 90 degrees move to the left, yes. So it's opposite world here. Minus means right and plus means left. Okay? And that's because the format is minus c, x minus c, okay? Okay, there's a lot in this lesson. This is a lot. But it's as easy as A, B, C, D, guys. Okay? A, B, C, D. It's easy. So what we're going to do now is we're going to try and put all this together so that we can look at a graph and that we can identify its equation. And again, if we look at A, B, C, and D, just those 4 things, if we get the right numbers, we can write an equation for the graph. Okay, so in this example, we're going to find the equation for this sinusoidal function here. And we are going to try to figure out what A is, what B is, what C is, and what D is. And then we're going to put it all together. And I've got, see this format for the equation. I'm going to put my A value here, my B value here, my C value here, either plus or minus something, and then the D value out here. So that's where we're going. So we're going to try and build this equation. Okay, so let's just start with A. Usually you can start with A and you can move all the way over to the right. Start with A. You know what? Honestly, to find the A value or to find the amplitude, probably going to be the first and easiest thing to find, I guess. So we'll start with A. So we have a maximum point here that this reaches at 5 and a minimum of -3. So from our work last time, we could figure out pretty easily what the range is from -3 to 5. That's actually 8 units, right? From the maximum to the minimum, that's 8 units. So the amplitude is going to be half of that range value, right? So what's the amplitude going to be? It's going to be 4. So A is going to be 4. You guys okay with that? All right. Now, do you need to know what the midline is? Yeah, we're going to need to know what the midline is. The midline will actually help us with D. And I'm okay if you find D right away, but you know, whatever, you don't have to. Honestly, I think that D might be a good one to do next because you've already kind of found A. So if A is the amplitude, what you can do, guys, is go from the max down 1, 2, 3, 4 units, and that should be your midline. You see that? And so your midline is going to be y equals 1. All right? Now we know that a regular sine graph has a midline at 0. So if we had to move this graph up 1, that means that D is plus 1. So D is 1. You see that? So that's what I was kind of like working through in my mind before. You can do A, B, C, and then D, but you know what? D is pretty easy. Once you got A, you can get D. Or get D first and then get A. I don't care. Okay, so B. Now, B we know is the period length. Okay? Now, you could find the period length pretty easily by, just taking the distance from this peak to this peak and done. But that's the period length. That's not B. So this is what we have to remember. When finding B, we have to remember that the period length equals 2 pi over B. That's what connects B and the period length. And so if I rearrange this equation a bit, cross multiply here, I get B equals 2 pi divided by the period length. And that's how you're going to find B. Okay? Very important. This is maybe kind of the least logical part of this. But because B is related to the period length in a certain way, we can find out how to solve for B by taking 2 pi and divide it by the period length that we see. Now, this is in degrees. So here's another thing we're going to need to notice. Do you see how this is degrees? This is not radians. So guess what? The B can also be written as, what's 2 pi in degrees?
360.
Thank you. 360 degrees divided by the period length. So we are not necessarily going to use this radian version. We're going to use the degree version. All right, now we're in business. Okay. So can we figure out what this period length is? This is 90. And then 1 full period over to here. What's that? Well, each of these are 30. So that looks like it's 210. Right? 210 degrees. So what's 210 minus 90? What's that, you figure? About 120. Excellent. So the period length is 120 degrees. So guess what? Way over here, the B value is 360 degrees divided by 120 degrees. And that's going to be 3, isn't it? So there you go. We've found our B value, and it's 3. We got A is 4 and B is 3. You guys good? Follow me there so far? All right, we know that this graph has been moved up 1, but what we don't know is how far this graph has been shoved over left or right. Now, it should be noted, guys, it should be noted that you can have 2 different C values and still have the right answer. There are multiple different C values because I can move a periodic graph, one that repeats itself. I can move it over this way and make it the same, or I can move it back and make it the same, right? Because they would overlap both ways. So what I suggest to do is to find your midline, which is 1. Find the point that looks like the start of the sine graph, and then find, you know what I mean, the end. So isolate 1 cycle of the sine, all right? Because now you can say, hey, this should start right here at 0, 0. But I know that it's gone up 1 unit, so that's where D comes from. D is 1. It's gone up 1 unit to this level. And it's gone over how many degrees this way? Well, let's see. 0, 30, 60. So this point that I've identified as sort of the start of the sine graph is moved to the right 60 degrees. So if the graph is moved to the right, that is a positive C value. Now, it's going to show up in the equation as a minus 60, but we've got, if you look at it just this way, we're moving to the right 60. So C value is actually positive 60. The D value is positive 1 because we moved up 1 unit. Okay, are you with me with the C value? Any questions on the C value? Is that a hand or no? Okay. You guys are all good? Okay. So we've got the A, got the B, got the C, and got the D. It's now just as simple as taking our format, our graph equation format, and plugging in our values. Easy as that. So the A value we said was 4. The B value is 3. The C value is 60, so this is going to be x minus 60 degrees plus 1. And to get rid of those silly boxes, it's going to look like this. Y equals 4 sine of bracket 3 bracket x minus 60 bracket plus 1. Okay? Now that is a perfectly correct answer. I will, though, however, show you that this could also be written like this. You see all these little brackets in here? That 3 could distribute to each of these. So this could also be written as 3x minus 180. If you don't include the inner brackets, you could see it like this, and that would be correct as well. The reason why Mr. Maxwell teaches you about these inner brackets is because when you put your C value in, okay, we don't have 180 in there anywhere, right? So you put your C value in here, and then if you want to multiply these out to show this a little simpler, you go right ahead. But in this format, this 180 is not your C, so you have to be careful. If there's a number other than 1 in front of x, you're going to have to factor this, okay? Take that 3 out and write it as 3 times x minus 60. That's your C value. Okay? All right, that's a big lesson. Okay? You guys did well, though. It's a long, big lesson. What I'm going to do is I'm going to get you guys to do some practice here. So here's your assignment. Here's your assignment that I'm suggesting for you. 1 to 9, 12, and 14. And I will flip over to the textbook here in case you need to see this. 1 to 9, 12, and 14. So I'll just run through, show you some of these questions here in case you forget your... Oh yeah, here's the in summary as well. So please take a look at that. Please take a look at this. This is everything that we've done here so far, finding A, B, C, and D, including period length and how that relates and so on. So spend a moment to look at that as well, but here are your homework questions.